Okay, great. Well, it's a great pleasure to be here at KITP to see so many familiar faces and kick off the meeting. It'll be an exciting week for sure. My task and what I decided to talk about today is to focus on massive galaxies at cosmic dawn. While there have been a number of surprises, I think massive galaxies has been one of those great surprises from JWST, so wanted to dig into it. So if we look at the consensus on the star formation rate density of the universe prior to JWST, there's this nice plot from Pascal Oesch showing the star formation rate density and its precipitous drop at redshift 9 and 10. These are, the cutting edge samples of what we had from HST, and there was really a dearth of objects at redshift of 10. And if you think about it in detail, this was more or less aligned with what one might expect from the growth of the halo mass function itself if you assume a fixed rate of conversion of baryons into stars within those halos, so a fixed efficiency. But as Rachel has alluded to, of course, JWST has given us plentiful surprises. Among those, the overabundance of very luminous galaxies at very early times. So this is just, one compilation that illustrates the point that there are a number of galaxies out to very high redshifts, spectroscopically confirmed out to redshift 14 or so now, that show us that the early universe was indeed very active. In the early days of 2022, we almost wanted to throw out our cosmological model, lambda CDM, because we found galaxies that were too massive to fit within lambda CDM. In this plot shown by Mike Colchin, but also Andrea Wavell, you see galaxies that are so massive that they couldn't have possibly assembled so early. Now, some masses, of course, have come and gone. A lot of those masses have, individual sources have been rebutted here, but the trend overall persists that there is an overabundance of these massive early galaxies. Here, this is just showing you a slightly different version of that from the number density of galaxies as a function of redshift and the mass density of galaxies as a function of redshift, where these curves represent more or less equal efficiency of converting baryons into stars in halos. And it is true that the largest tension exists from the most massive systems here. The term efficiency has been used really widely over the past few years, and the definition of efficiency varies by user, so I just wanted to dig into that a little bit. Of course, what we're trying to capture here is the relationship between dark matter halos and the stars within those dark matter halos. That can be captured in terms of the stellar baryon fraction, which is just the stellar mass over the cosmic baryon fraction times the halo mass. This is more or less the integrated efficiency of the star formation process over the history of the halo. You can also capture this in an instantaneous measure, the time derivative, so star formation rate over the baryon fraction times the halo mass accretion rate. But if you talk to anyone who's worked on the star formation process, you know that this process is fiendishly complex, and certainly you can't cut out the middleman, which is cosmic gas or primordial gas, which eventually leads to the formation of molecular hydrogen, which then in turn leads to stars. Now, you can capture the star formation process of this bottleneck between the gas and the stars differently in terms of capturing the star formation rate per unit gas mass, which, empirically in all of our measurements of the nearby universe does not really typically exceed 10% or so. Or you can characterize it in the free fall efficiency, the star formation rate over the gas mass per free fall time, averaging around 2%. So what I hope to illustrate here is that this process is really a bottleneck to the entire relationship between dark matter halos and the stars contained within them. But at the root of all of our debates about efficiencies is the issue of whether or not we believe the stellar masses of these galaxies. It's a fundamental question, and it's a complex question. And if we do believe their stellar masses that are implied to be quite high, what conclusions can be drawn from the star formation process and baryonic processes inside of those early halos. Now, I like to illustrate the reason that massive galaxies are uniquely useful for answering this question. So this is an animation of the halo mass function from redshift 20 to redshift of 8. And I've highlighted 3 different masses here, 3 different halo masses. And you can see that there's a dramatically different rate of doubling here for the 3 different mass spins, such that for low mass galaxies with stellar masses around 10 to the 7, you increase by maybe 3 orders of magnitude between redshift 20 and redshift 8. But at high masses, 10 to the 9 solar masses, you've increased by a factor of 7 orders of magnitude. 7 orders of magnitude. So that illustrates that if you can find these massive systems with 10 to the 9 solar masses of stars very early, beyond a redshift of 10, you're really starting to press into a regime where individual sources can be uniquely useful for understanding baryonic physics at early times. Massive galaxies are bright. They are also rare, which motivates the reason to look for them in wide area surveys. So I'll just put on my Cosmos hat for a moment here to advertise, this was really the motivation for the Cosmos Web project. Our mosaic is finally finished. This is the mosaic shown with respect to the scale of the moon on the sky. This is a mosaic that is 3 times larger than all other JWST deep fields combined. And we have about a million galaxies detected in the image. Just to give you a sense of the image, I'm going to zoom in a few times. You can't appreciate it unless you zoom in. So zoom in once, twice, 3 times here. This focuses in on newly discovered Einstein ring, the highest redshift Einstein ring. The lens is the highest redshift lens known. I'm not going to talk about that today because we're talking about cosmic dawn, but it just gives you a sense of the scale of the image. Now, the landscape of new discoveries from JWST have been profound. Here I show the compilation from Kevin's paper, from Jade's, of the vast array of candidates we have out to redshift 12, 14, from new JWST surveys. But I want to show you where Cosmos Web sits in that. We're adding to the bright end the luminosity function, galaxies as bright as -21, -22, with a number of candidates as bright as GNZ11, GHZ2, the redshift 12 source, and even the redshift 14 Jade source. Plotted a different way, here now on stellar mass versus redshift, and so I've inverted redshift here to show you the landscape of literature stellar masses that have been reported. Both photometric and spectroscopic samples of high stellar mass galaxies have really pushed the limits of what can be formed in lambda CDM. So just to contextualize, this curve here shows you the curve that corresponds to the most massive halo in the entire sky, assuming all of the stars have been converted, or all of the baryons, excuse me, have been converted into stars. So this is exceptionally unrealistic stellar masses. But if you lower that curve a little bit, this is a representative of 0.3 square degrees. That's more or less order of magnitude what has been published in the literature in terms of candidates from JWST surveys. You see that a number of these sources kind of start to butt up against the limit, assuming we have converted all of those baryons into stars. So it's really quite exceptional, some of the reported stellar masses exceeding 10 to the 9 beyond a redshift of 10. Now, the galaxies that are giant points here, giant circles, those are all spectroscopically confirmed, including the 3 that I highlight in color as exceptionally massive and bright systems. Now, if we take that bottleneck of the efficiency of converting gas into stars, you notice that many of these sources exceed that limit. If we extrapolate that and put that maximal 10% efficiency of turning gas into stars onto this plot, then we get something shown in this purple exclusion area. So any source in that zone is exceptionally efficient. Now, of course, the masses, so do we believe the masses? How do we explain these high masses? Now, they could be wrong, so let's count the ways in which they could just be wrong. Anyone who's, thought deeply about calculating stellar mass has known that it's a fraught business, and you need a close understanding of the star formation history in order to really constrain this. To 0th order, the star formation history, of course, gives you a mass to light ratio. That's simply, so you can convert MUV into stellar mass. But for these sources beyond a redshift of 10, when we look with NIRCam data, we only have the rest frame UV, and that is, one thing you learn in grad school never to do is to derive a stellar mass from rest frame UV, but nevertheless, we're doing it. Ill-advised, perhaps. Now, of course, there's also this phenomenon of outshining where you can get orders of magnitude difference that affect the stellar mass estimates. If you have recent bursts that, for example, can outshine earlier episodes of star formation, that could lead to the underestimation of your stellar mass. But all of this is tied into the understanding of the star formation history, which, of course, is fundamental. I do want to point out a counterpoint here. Now, as uncertain as the star formation histories are, the star formation history beyond a redshift of 10 for the luminosities that we're talking about is actually severely limited. It's not a huge dynamic range you can have. So here's just a cartoon star formation history of a luminous redshift 9 galaxy. If you assume most of the stars formed, 200 megayears in the past, then you get 1 stellar mass. If you assume that the stars have formed more recently, then the stellar mass estimate lowers given a fixed MUV. And if you assume the most recent burst, then the stellar mass is the lowest of all. Now, even if you assume the most recent burst, in many of these systems, the masses are still quite high. So that, there's not a lot of wiggle room to assume any different star formation history. Now, we could be wrong because we're not actually looking at stars, of course. We may actually be looking at AGN or nebular continuum. So this is a plot by Roberto Maiolino for the GNZ11 system, positing that its light is dominated by an AGN. Now, of course, this is a very real possibility. If it's not a high stellar mass, if we're not really looking at stellar light, then we are looking at a supermassive black hole. And I think we'll hear many talks about that as a possibility for systems like this later today and later this week. But it's really a separate problem. So I'll defer to the black hole talks on that topic. Now, nebular continuum is an interesting proposition here that you're dominated by, 2-photon emission from neutral hydrogen. That would be consistent with more massive O stars, hotter O stars, which produce this nebular continuum. Now, that's not impossible, of course, but, given our conventional IMF assumptions, it's a little outside of the box. You could change the IMF altogether. Now, the IMF is truly the house of cards on which we build everything, and it should, frankly, there are many good reasons to believe that it is quite different beyond at very high redshifts. For example, the universe's metallicity is much lower, known to be lower at high redshift. And of course, low metallicity leads to a more top-heavy IMF, and that lowers the mass-to-light ratio substantially. Now, if you consider what factors might be practical in tuning the IMF, you might be able to make up for half a dex in mass difference this way, but there are also some nuances there that are not clear. Like perhaps, you can't make up a lot of mass here because if you have a top-heavy IMF, you're more prone to higher feedback from stars, those massive stars. Okay, so there are many ways in which they could be wrong. They could also be right. So if you consider so there are, certain conditions under which you might expect to get dense nuclear starbursts that have little regulation from feedback on short time scales. So talking about time scales less than 10 million years or so. And if you have several of those, with, in very dense giant molecular clouds. These are some really nice results from the fire team, showing that on occasion you get these conditions where you have very high efficiencies of converting gas into stars, then you could build that much mass that quickly. This relates, of course, to the feedback-free star formation model by Avishai and others as well. And to tie that in to the discussion about stochastic star formation, which has been coming up in the literature quite a bit, that there is a consensus that you can you can produce excess UV luminosities substantially through these very recent episodes of starbursts and perhaps super Eddington luminosities, and you're expelling things like dust, which obscure the UV. And this is the nice model by Andrea, where you have an episode of obscured star formation and then blow it out, and you expose more UV luminosity that way. Okay. So there are all of these, complexities to our understanding of the stellar masses. But if you look observationally where we are currently, if we're talking about this exceptional luminosity class beyond a redshift of 10, we have 3 examples that have been spectroscopically confirmed. GNZ11, GHC2 at redshift 12, and then the JADES redshift 14 source. And when I look at these, first when I look at the redshift 14 source, I think immediately it had no business even getting a spectroscopic redshift in the first place because of the nearby contaminant. And so, it brings me a lot of optimism that we have so much to learn about these early universe giants. We're just scratching the surface because spectroscopically, these are all quite distinct. Some host an array of high ionization lines, some don't. We have a lot of questions to answer, and I think we can only really dig into that by confirming more of these sources that will help us answer whether or not they're dominated by AGN, if they're attenuation-free, if we believe the stellar masses at early times. Observationally, I do want to, just point out that there has been a persistent bias that, I think the community has been a bit conservative in selecting the absolute bluest objects to spectroscopically confirm. That is, of course, because those are the most robust to low redshift contaminants solutions. So, we shy away from these slightly redder high redshift candidates because the possibility that they're a low redshift interloper is, a couple % or so. But given the efficiency of near-spec MSA, I think we're in a regime where we can start to confirm both simultaneously, and it should be done. Okay, so I want to step down a little bit in redshift now to redshifts greater than 5. If you ask what are the most massive galaxies in that regime, you land at little red dots. Okay, so I want to talk briefly about the little red dot population. And these are the universe breakers, the initial universe breakers that were doubly selected via a Lyman break and a Balmer break, and found to be very high stellar mass objects if you assume the light is stellar. But quick spectroscopic observations from the community a few months later from many in this room showed an overabundance of broadline AGN. You have broad and Balmer lines, which is, of course, indicative of the broadline region, suggesting, in fact, the light was coming from supermassive black holes. But it's a conundrum that we're still debating today, and I'm sure we're going to hear a lot about it this week. They seem to lack X-ray emission, which is, a hallmark of AGN. And even in a stack, a very deep stack on Chandra Deep Field South, they lack this X-ray emission. They also lack mid-infrared emission from hot, dusty torus that you might expect around AGN. So the debate continues. Some also have detected strong Balmer breaks consistent with continuum emission from stars. So it's a little unclear. Still, we're swirling around this issue of whether or not their light is dominated by AGN or by stellar processes. I wanted to summarize this conundrum from the perspective of this paper by my graduate student, Hollis Aikens, that was out earlier this summer, which really took a sample of 400 or so little red dots from cosmos and played the thought experiment of assuming they're all AGN, they're all star formation, and then playing out the repercussions and trying to understand in detail in this field where we have a really good feel of their volume density. So the conundrum here is that if you assume that all little red dots are AGN, then you end up with a tremendous overabundance of supermassive black holes relative to pre-JWST expectations from the quasar luminosity function. And on the other hand, if you assume that their light is stellar, then you have many of these galaxies whose masses really push the limits of what you can form in lambda CDM. And that issue of the efficiency of converting gas into stars. Now, the premise of this thought experiment is that even if you split the difference, assume half are AGN, half are star formation, you're not solving the problem. A factor of 100 divided by 2 is 50. You still have to explain a factor of 50 overabundance of supermassive black holes. So just to add to the mix of complicating the story, I wanted to show this plot. It's actually from one of Phil Hopkins' papers, showing the stellar mass surface density as a function of stellar mass across a huge dynamic range from local globular clusters up to the centers of massive elliptical galaxies in the nearby universe. And you see this empirical maximum here around 10 to the 11.5 solar masses per cubic per square kiloparsec. Little red dots, we often think of, a line of evidence that they're AGN as being that they're spatially compact, that they're unresolved. But unresolved point sources don't necessarily mean that they're AGN. In the Cosmos Web sample, we see that 95% of these sources sit in a regime where they could be dominated by stellar light, very compact stellar light. Hollis in this work did a heroic effort to stack all of the multi-wavelength data we have in Cosmos on all 400 little red dots in his paper, putting together this compilation. And what we found, in short, is that little red dots are only found in JWST data. There's no X-ray emission in a deep stack, so consistent with what's found from much deeper X-ray data. There's no evidence of a mid-infrared power law, so lacking that canonical dust SED in the middle. And then no submillimeter dust emission at long wavelengths, which also kind of points to the possibility that these are perhaps not dominated by dust-obscured star formation. This SED kind of represents the maximal SED you can get that's compliant with these limits. So I just wanted to, before I end, speak briefly to where the dust is in little red dots. And I'm sure we'll have a variety of thoughts on this as well. This is summarized in a paper earlier this summer. And if you take the canonical cartoon picture of an AGN, here you have an accretion disk on AU scales. You expect the torus to exist on parsec scales at temperatures roughly 1,000 Kelvin. Now the dust sublimation temperature is around 1,500 Kelvin, could be 2,000 Kelvin depending on dust grain composition. If you plot that 1,500 Kelvin SED, you expect to see this emission in the mid-infrared. So this is the puzzling component that has been missing in current observations. Now you could say, well, if it's not in a torus, maybe the dust is in the ISM on much larger scales, on 400 parsec scales, and maybe it has a dust temperature of 30 Kelvin or so. If you assume that, you would get this blue SED, which butts up against ALMA detection limits for, nominal depth, not super deep observations. Those are shown by those gray bars. But after going through the thought experiment of thinking where the dust could be, it's not detected on either end, we came to the conclusion that the dust in little red dots has to be around 100 Kelvin and is not massive at all. It's rather modest in dust mass, with 10 to the 4, 10 to the 5 solar masses of dust. And the reason that is because these sources are so spatially compact. You can't hide 10 to the 6 solar masses of dust very easily in such a compact source. And this is consistent what is found in this work by Lee et al., and I think Kohei might talk about it later, coming at it from a completely different angle of modeling AGN torus emission of little red dots. Instead, considering a different attenuation law, you can get 100 Kelvin dust that way as well. So these are roughly consistent, arriving in completely different ways. I don't have time to talk about it. We had a thought experiment of searching for not so little red dots, not compact little red dots. I encourage you to check it out. This paper by Fabrizio Gentile. And the very last thing I'll remind you of, we've talked about the efficiency of the star formation process, but not all baryons are stars. We've been swirling around this issue of stars and stellar masses because that's what JWST gives us. But there's a tremendous tool we have in ALMA in that it can actually, if you get dynamics of lines like C+ or O3, you can start to place interesting constraints on this efficiency argument by measuring dynamical masses in ways that are challenging to do with JWST itself. So I encourage you to think about that more broadly. And I'll leave you with my summary here. I think we're really at a rich time of understanding these UV bright galaxies that are particularly massive, but we're really just scratching the surface, and we have a lot of work to do in understanding what they're made out of. So I hope that we're able to see ample observations of these coming up in the next few cycles. Thank you.
For that wonderful talk. So the one thing I did not think to arrange ahead of time is people to help me with the microphones. So would anyone like to get a little exercise?
Oh, Andrea wants exercise.
Yeah? You can help? Fantastic. Thank you so much. Okay, so while we get our, I think there's one there and one there. Oh, and looks like Benedetta is also volunteering. So you can do it next time, Andrea. Thank you so much. Okay, do we have questions? Yes. Yes. That's the one. You can just take it out of the thing. Perfect. Do we have questions for Caitlin?
Yeah, sure.
Please wait for the microphone.
Just a very naive question from a particle physicist. Could you remind us what little red dots are?
Oh, yeah, well, I didn't explain it, did I? Yeah, so little red dots are the phenomenon of JWST in many of its data sets has revealed a population of galaxies or black holes, unclear. These sources, point sources of light that are very compact, unresolved, and they are particularly red. So they have not been detected by Hubble or any previous telescope, and they only show up at the longest wavelengths. Yeah.
Other questions? I know it sometimes takes a while for them to form. Marta, you have the mic. You're ready to go.
I make it easy. So perhaps we will cover this later, but you focused on the extremes, really, the most massive. But so if you were to assume a continuity, so from high redshift to low redshift, I mean 6 or 7.
Yeah, sure, low redshift.
Yeah. So if you want to assume a continuity, so the population can be explained by a single picture. So if you discard this extreme, do you feel that there is a problem, or do all these sets of problems, star formation, efficiency, AGN, and so on and so forth, do they disappear as you go to the bulk of the population, say L star, or do they continue?
Yeah, well, I think other talks will address the bulk of the population. I do think speaking for the extremes, though, I think the extreme shifts as you step towards lower redshift. And there are many of these problems that have been open, since before JWST as well, like the formation of these massive star-forming galaxies that are highly dust obscured. How do you assemble 10 to the 9 solar masses of dust at redshift 6? So it's possible that, you know, by probing at least the extreme end across, you know, redshift 5, 6 out to redshift 14 or so, that could form a coherent picture that would be interesting in terms of, you know, these UV luminous sources being progenitors of perhaps these luminous dusty sources at later times. But you know, there's so much uncertainty in drawing those links that it becomes difficult when we haven't even, you know, fully captured the relationship of the UV luminosity function to the IR luminosity function, et cetera. So lots of work to be done.
Other questions? I think I see one back there. Nick?
Yeah, sorry if it's a very uninformed question. If you take a little red dot and put it at redshift 0.1, what would it look like?
Yeah, that's a great question. Would the host galaxy be visible? I would hope so. There are a few examples of fairly like low redshift, little red dots. There's one at like redshift 2 or so that looks fairly consistent, where it has a UV uptick and a highly obscured, you know, rest frame optical spectrum. There are examples, though they are exceedingly rare. So yeah, they exist down to redshift 2 or so, not redshift 0.1. But I think, you know, that is an area that would be really beneficial to dig deeper in terms of identifying these lower redshift analogs and seeing if we can identify host galaxy emission underneath the point source emission of the little red dot.
Okay, Alice.
Thanks, Caitlin. Okay. Thanks for your talk. Hey, so I want to leave little red dots for a minute, if that's okay.
Yeah,
okay.
Yeah. I'm sure we'll come back.
Yeah, I'm sure we will. So you were talking about ways to sort of get out of the high masses that are inferred for some of the early sources. You mentioned playing around with the IMF, which is, you know, often discussed as a possibility. But you were talking about in the context of low metallicity in the early universe. I guess I wanted to push back on that a little bit because presumably the galaxies that are the most massive are actually not going to be particularly metal poor.
Absolutely.
So maybe
I agree.
Low metallicity is not the argument I put first for a different IMF.
Oh, absolutely.
But there might be others.
I totally agree because I think that argument works okay for these like lower luminosity sources that, you know, folks have been discussing. But as you say, going to the extreme, you expect, you know, much more enriched environments. Yeah, I concur.
Sorry, I'm not sure who had their hand up first, but let's maybe go to Kohei, and then Lars, did you still have something?
Thank you, nice talk. So the color selection of little red dots kind of unique. Like, you know, you impose kind of V shape, but I'm wondering if you relax some assumption like a UV slope, for example, do you expect more like little red? You might observe more large fraction of little red dot-like sources. Yeah. That might be more, you know, serious in terms of the luminosity function if they show a broad-line emission.
Yeah, so I didn't even have time to discuss that, but the little red dots that we look at in Cosmos, we're not selecting the V shape. So we actually, I personally don't believe that the UV emission in little red dots is fundamental to you know, for example, if it is a geometric, it could very easily be a situation where you have a highly embedded source and a little UV light leaks out due to a patchy dust geometry. In that case, it's certainly not fundamental. If it's an attenuation curve revision, then it would be more fundamental. I think that needs to be dug into more, and you know, we need these large statistical samples to do that.
Thank you.
Okay, Lars?
Caitlin, there are a class of very luminous, superluminous supernovae that are minus 20, minus 21. So when I see objects that bright, my question is, do you have anything knowing about time variability on a 1-year time scale?
Yeah, not yet. Not yet. Wouldn't it be great? Yes. Yeah, it would be great to get more time domain constraints on these.
So my other question then is, so how rare are they relative? So if they happen to just be a massive galaxy which has that supernova happening in it, what rate would that need to be to explain? You know, they look to be very rare. So my question is, are they 1 in 50 out of a population that's 100 times?
That's a great question. I think, well, Roberto did this. I'm staring at you in your paper, right, on GNZ 11. And what was your estimate? It was like how much can supernova contribute to the total light? It's like 10%. Or sorry, I'm just pulling that. low. But I mean, does that account for superluminous supernovae? Yeah. Okay.
Can you repeat what Rebecca, if you could hear it?
Yeah. So Roberto found in his analysis of GNZ11, that was GNZ11, right? Sorry, too many papers. No, the AGN. Okay, that it's minimal. Go ahead.
Yeah. So we explored two things: the variability, which is only few are seen to be variable, and the upper limit on the variability set a constraints on the contribution from individual supernovae and the cumulative effect of multiple supernovae. And even if you allow for a factor of 10 or 100 higher luminosity that is typical of hyperluminous supernovae, still doesn't make to have that luminosity. Also, the supernova rate that you would require to explain all of these object AGNs or little red dots is so high that you would expect to see the associated X-ray emission in the X-rays at more than 3 sigma. So the non-detection of the X-rays plays also against the supernova scenario as well as other scenarios.
Okay, great question. So let me ask Seiji to come and set up, and we can take a few more questions while he's getting set up. So let's get Rafa, and then we'll get the questions over here if we have time.
Yeah, so just a quick comment following Alice's question before. So I think that Soo-Myeon Chon will show simulations in the next few days in which we actually find that at high redshift, even if you are relatively metal rich, means 0.1 solar or even solar, because of the increasing temperature of the CMB, you do expect deviation from the IMF. So then it's a question if this is enough and what are the implications. But in terms of metallicity, when you are above redshift 10, this is not really a serious issue according to the simulations.
Okay. Joe?
Could you just comment on there seems to be a continuum of reddening in objects that have broad lines identified in JWST spectra, and the little red dots would be then on the extreme end of that. Can you comment on the relationship between, say, little red dots and bluer things? They're not as compact, but I'm just saying there's a class of objects that have broad lines that have a large range of reddening.
Yeah. I personally haven't thought a great deal about it. What's the volume density of the bluer things? I mean, is it?
Roberto can answer, but I think it's a few % of galaxies,
yeah.
So it's not. They're more abundant. They're not as red, but it's the
right.
same deal of just a single broad line and no other evidence for an AGN. So
yeah, exactly. No, it's a good question. I don't have any particular insight on that, but Yeah, I mean, I think a lot of this, in terms of the little red dot population, we need to try our best, to get dust continuum detection from ALMA. That might help contextualize where the dust is, where it comes from, and how it would relate to the less obscured population. There are also interesting, dynamical arguments that you could get broadened lines without an AGN, right? Through kinematic broadening. But lots of ifs in that scenario as well.
Thanks.
Okay, with apologies to Mark, I think we should thank Caitlin again.